Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hi there, thank you for joining us once again on the Space Nuts podcast. My name's Andrew Dunkley, your host, and with me, as always, Dr. Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. I'm still at large. They haven't found me yet.
I think they've given up looking.
Yeah, they probably did many years ago. That's right. Quite right, too.
Now, today we've got a few interesting topics. One that's certainly caught the media by storm, and we'll look into that being the Space Doogie. This is the exo asteroid that passed through our solar system last year. And we've sort of been able to figure out where it came from, and there's been a few questions about it, and now they're starting to think it might not have been a rock, it might be something else. At least a few people think that. We'll look into that. We'll also answer questions from Ryan in Delaware about exoplanet detection, and Gordon's asking about seeing things that no longer exist in terms of light detection. So those are two interesting questions we will tackle today. But first, Fred, they have more or less confirmed that in the middle of the Milky Way galaxy there is a supermassive black hole full of biros.
So that's where they go.
That's exactly where they go, I'm sure of it.
Okay. All righto. So this is a sort of ongoing project, Andrew, that you and I think have spoken about before, but it's just taken a kind of quantum leap forward that really, it is the definitive proof that what we're dealing with in the center of our galaxy is a supermassive black hole. Not that any was needed, to be honest, because the previous work really demonstrates that. Let me just recap briefly. When you look at the Milky Way, you're looking through the thickness of our galaxy, the Milky Way galaxy, a swirling disk of hundreds of billions of stars and gas and dust and all that stuff. We see the center of our galaxy in the direction of Sagittarius, which is certainly the richest part of the Milky Way, but it's also very dusty. So in order to penetrate that dust with telescopes, you need to move from the visible region of the spectrum into the infrared region of the spectrum. And scientists over a very long period of time have been using the VLT, the Very Large Telescope down in Chile, to actually look through the dust and see see stars which are in orbit around an object in the dead center of the galaxy. A thing, by the way, that we give the strangely weird name of Sagittarius A star to. Sagittarius A star is a radio source, and it's written just like that, Sagittarius A and an asterisk. It's always been called Sagittarius A star. I think it was to distinguish it from another radio source nearby, but Sagittarius A star is the one that we associate with the galactic center. Okay, so that position coincides with something that's very dark in infrared spectra, but there are stars around, in the infrared wave band, but there are stars around it, and those stars have been observed for 20 years or so, and you can plot their orbits because you can sort of, look at great detail in this region of the center of our galaxy. And there's a group led, if I remember rightly, by Reinhard Genzel, who's at the Max Planck Institute for Extraterrestrial Physics in Germany. That group has been studying this swirling group of stars going around the galactic center. And actually, the dynamics of them, when you plot their orbits and everything, that also tells you that there's a 4 million solar mass black hole in the middle, mainly because you can't see it. They seem to be orbiting around nothing, which always looks a bit weird. But that's because the black hole is not visible in infrared. However, There is an instrument which uses the Very Large Telescope, and by the way, the Very Large Telescope is 4 telescopes actually, 4 unit telescopes as they're called, each one with an 8.2 meter diameter mirror. They're very big instruments, but there is an instrument, there is a way of using them together, combined with some smaller auxiliary telescopes, that lets you carry out something called interferometry. And interferometry is a way of observing things over very short distance scales. By that I mean to actually observe the finest detail in distant objects. So they've used this technology, and now they are looking not at stars orbiting the black hole, but at the accretion disk of the black hole. That's the disk of swirling material around it, which is the last thing that happens before stuff gets sucked in to the black hole itself. They've actually been looking at infrared flares from this region. So as this gas goes round, it's excited into emission. Actually, partly by magnetic effects within the with the black hole itself and within the disk of swirling material, and so you get these infrared flares. And with this sort of super duper interferometer at Cerro Paranal, where the Very Large Telescope is, they've actually been able to observe these flares moving around the black hole in something called the innermost stable orbit. That's to say, they're seeing things that if they were any nearer to the black hole, they'd get sucked in. They'd be on the event horizon. That's the horizon beyond which we can't see.
They're as closest to the drain hole as they can get without before getting sucked down.
Without being sucked down, that's right. And so the observations that they've made, first of all, they confirm that this accretion disk is nearly face on to us, and that sort of ties in with the way the stars are swirling around it too. So the accretion disk is face on, and what that means is that they've been able to watch things move around it at something like 30% of the speed of light.
That just blows my mind.
It is mind-blowing stuff, but there is a lovely confirmation in this as well, and it sort of harks back to something we were talking about last week. We were talking about polarization last week in regard to the 2 dust clouds around, orbiting with the moon. Polarization has been used also by the scientists looking at the black hole in the galactic center, because you would expect the light from it, from these infrared, flares, to be polarized. It is, and the polarization itself also rotates, which is what you'd expect as these things are carried around the black hole. So really staggering stuff. Once again, the calculations all point to a supermassive black hole 4 million times the mass of the sun, which is now pretty well done and dusted. What I think we've got to wait for, and you and I have spoken about this before too with some excitement, is the results from the, what's it called, the Event Horizon Telescope, this radio telescope that wants to actually try and image the black hole itself. I think we're still waiting on news of that.
So it is focused on this particular black hole.
Same one.
Sorry?
Yeah. Yes, it's the same one.
Yeah,
That's the same black hole that is being observed.
Okay, so we still can't or haven't seen one, but we're hoping that we will now be able to. And it's a strange thing, isn't it, where we've got all the data that proves that something exists, and yet we have never seen one. Everything just is there to say that thing is in existence, it is right there. We're looking at the place it is, but we can't see it.
Yeah, well, that's correct.
And it's otherwise known as the balance of my bank account. But,
yes, the stuff that you're looking at that you can't see.
Yes, exactly.
Well, in your case, it's because there's nothing there.
No, you can't photograph it. Okay, so if they're getting ready to try and give us a look at this thing, when might we expect some result from that?
Well, the observations, as I understand it, let me just check up on that. The observations were made last year. We talked about this some time ago. I think we talked about this in July. We talked about the Event Horizon Telescope. But the observations were made in April 2017, and we, as far as I know, the numbers are still being crunched from all that. There's still compiling the data, image rendering, comparing models, and things of that sort. I don't know. I think my guess now is that it will be in the new year before we get these results. I think if there's something dramatic, what will happen is that the scientists will wait for a time when there aren't elections taking place in the USA and things of that sort happening that's soaking up all the media's attention.
Yes.
Yes. There will be an announcement. I don't have any inroads. I don't actually know anybody directly connected with this, so I don't have any, back room gossip about when it might be. But I will keep my ears open. If I hear anything, I'll let you and our listeners know.
Indeed, we can't wait to see it. It'll probably just look like a black hole, I imagine, but we'll find out, I hope.
It'll look like your bank balance. It'll be black and not
actually,
really there.
Mine's much bigger. Okay, you're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by Tech Radar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments, and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, we turn our attention to a big pile of doogie in space. This is the rock that passed through our solar system last year, and it was sort of past us before we realised it was there, and then they investigated it and discovered it wasn't one of ours. It had flown in from some other galaxy or some other part of the galaxy. And it was determined to be a rock. It was an unusual rock. It was the shape of a doogie or a cigar, if you want to be a bit more appropriate, which I don't like being.
If you remember, Andrew, I likened it to a French loaf.
Yes, that's
which
right.
I think is probably the most culinary satisfying version of your analogues there.
The space baguette. But
space baguette, that's right.
And it's called Mua, which is what, the welcome visitor, or the guy who just went past and stole your keys without looking, whatever it is. But it's back in the news because there's now some speculation that it might actually be artificial. So, and the word alien has popped up. I haven't used that one myself, but it is being used. So where are we at here? Are we talking a big pile of doogie here?
Look, we're still talking about an asteroid, I think. Let's recap again. Oumuamua, a Hawaiian word meaning messenger from the first messenger from afar, I think, if I remember rightly, chosen because this object was discovered by a telescope at Haleakala on the island of Maui in the Hawaiian Islands. This thing passed through the solar system around about a year ago, October, November last year, and its velocity was such that we immediately knew that it wasn't something that belonged to the solar system. It passed through on a trajectory which brought it in from outside and will take it outside again as it carries on its journey through space. So very exciting stuff. It was the first interstellar asteroid. Now, there was some debate at the time as to what this object was. Was it an asteroid or was it a comet? And the difference between them is that basically asteroids are rocky, comets are icy. That's the bottom line, although comets also include a lot of dust in them. The weird thing is that it was long and thin, as you've described, so graphically, if I might say. It's something like 1/4 of a kilometre long, or 250 metres, or 250 yards or thereabouts, by about 40 metres, and cigar-shaped, and tumbling end over end, so that it had, I think it's got a rotation period or a tumble period of something like 8 hours, something of that sort. And it was that tumbling, of course, and the way its brightness changed that allowed astronomers to work out more or less what its shape was. What really sort of clinched the idea that it was an asteroid is that people observed it as closely as they could, given that it had already passed its closest to the sun, and indeed its closest to the Earth. They observed it to look for any evidence of what we call outgassing. This is material coming off the surface, which is typical of what happens to comets when they get reasonably close to the sun, and that the gas comes off and is excited to glow, which is why we think of comets as being these very bright objects traveling through our night skies. Excuse me. However, nothing was seen in that regard, and so the conclusion came that it was an asteroid, and in fact its colour, it's a slightly reddish colour, is also consistent with a rocky surface that's been bombarded for a long time, millions of years, by cosmic rays, the subatomic particles that really permeate the whole of space. So that sort of seemed to, put the lid on the discovery, except that there were slight peculiarities in its trajectory, and this sort of led to the idea of it being a comet being reopened, because it experienced some accelerations that could really only be explained if something was pushing it slightly. And so the suggestion is that perhaps it was actually outgassing. There were, there were plumes of gas coming from this thing which were providing an acceleration, changing its orbit very slightly. We can detect these things very accurately, Andrew. That's why little nitty-gritty things like this crop up. So that was speculated, although once again there was no sign of any cometary, outgassing. So what has now happened is a paper which has been produced by scientists at Harvard University in the USA, and I have to say that its lead author is let me just get
both getting phone calls. Its lead author, so everyone's got an opinion on this.
Yeah, indeed. Its lead author is somebody who's always a bit provocative when it comes to this sort of thing, and I'll explain that in a moment. But the paper is really about what kind of what could be causing this acceleration, and a lot of the paper is about the idea of radiation pressure from the sun pushing, this or giving this acceleration that Oumuamua seemed to exhibit. So that was the bulk of the paper. But right at the end, there is a little bit that says, what about speculating that this is actually a light sail, that this thing is an artificial spacecraft with a light sail which is receiving the sun's radiation, and that's causing it to accelerate. So the author of the paper or the authors of the paper immediately get into highly speculative regions. And has been a lot of commentary by other astronomers on this, saying, why do you go to the least likely explanation of this, of whatever this phenomenon might be? There was one comment
that gets attention. That's why it gets attention, and it gets you noticed.
Yes,
and the media's unwritten rule is never let the truth get in the way of a good story. So they've latched on to the least likely situation, and it's become the lead. That's what I reckon.
Yeah, one of the that's right. That's what it's all about. It's Avi Loeb is the chief author. He's actually the chairman of Harvard.
He's the doogie stirrer. That's who he is.
And he's a co-author. He's basically he's put this idea out. One of the comments that comes from an astronomer who's basically not connected with this research. Actually, somebody in Heidelberg in Germany. In science, he says, we must ask ourselves where is the evidence, not where is the lack of evidence, so that I can fit any hypothesis that I like, because that's effectively what's happened. So yes, it's certainly causes a stir in the world. It's got some publicity for the Harvard Astronomy Department and Avi Loeb, the chairman of that department. This scientist I might mention is also the one who speculated that fast radio bursts, which are something else that currently don't have an explanation.
Fast radio bursts.
That's the one, fast radio bursts. Yes, right. Exactly as we were speaking. That those are the result of aliens using lasers to propel light sails through the universe. He's very keen on the idea of light sails, and clearly brings them into any conversation where it seems relevant. Fair enough. I actually don't have a problem with that. I think it's good. It's good to put these ideas out there, and I think at the same time it's also good to realise that they are highly speculative, and may well be a long way from the truth.
But never say never.
But never say never.
Never
exactly.
say never. And light sails are being looked at as a viable transport option for long-haul space travel. We're even looking at sending some to Alpha Centauri, aren't we?
That's right. And in fact, Avi Loeb is actually an advisor on that project, which is, the Breakthrough Starshot project. Yeah. So There you go. You can see why he's keen on light sails.
For all intents and purposes and lots of tongues in cheeks, this is a rock.
Yeah, as far as we know, it's a rock. The problem is, Andrew, that because it was moving so quickly, there was no chance of mounting an expedition to send a spacecraft to chase after it and get photographs or anything. It came and it went, and it came and went very quickly. However, what it does suggest is that taking the hypothesis that this is actually an interstellar asteroid, a natural object that's escaped from some other solar system and has basically stumbled into ours and gone off on its way. What it does suggest is that these things are not totally rare, that we might well see. In fact, some people speculate of the order of one of these a year, and so we should be more prepared the next time there is one, and have a better set of telescopes looking at it and be a little bit more vigilant as to try and catch it when it gets close to us rather than when it's waving goodbye.
Very good. All right. Sorry to disappoint everybody, but it's a rock. You're listening to Space Nuts with Andrew Dunkley and, of course, astronomer Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, Fred, to some questions. We're going to try and tackle a couple today. If we do them by twos, we'll never catch up anyway, but we're going to do two today. And this one comes from Ryan in Delaware. I had a quick question about the exoplanet detection method known as the transit method. Because the transit method uses the slight dimming of a star's light to find planets, that presupposes that the orbital plane of the system is on edge with our viewing angle. Have we determined if the majority of exosolar systems have their orbital planes aligned with each other? Are they aligned to the orbital plane of the Milky Way? And for that matter, is our solar system aligned with the Milky Way? Thanks in advance and keep up the great work. Well, do we have to? But thank you, Ryan, for the question. What do you think? That's an interesting question about the observational angles of these events.
Yeah, it is a great question, and embodies a number of parts to it. The bottom line is that the answer to most of those questions is no. But let me start with the first one. Have we determined if the majority of exosolar systems have their orbital planes aligned with each other? So when people propose the transit method as a way of detecting planets around other stars, and remember this is because the planet actually passes between the parent star and ourselves, and then, of course, that means that in order for it to do that, the orbit plane must be at least reasonably well aligned. When people first proposed this, they looked at the statistics. In other words, they said, we expect orbit planes of solar systems to be completely randomly orientated. And so they did the statistics based on that and said, yeah, well, it's still worth doing it because there'll still be enough of these things crossing in front of their parent stars. And what we find, we now believe that there is at least one planet for every solar system, for every star. Mm-hmm. That's something we simply didn't know before. But when you do the statistics, you find exactly that the statistics match what you get if all the orbit planes were randomly aligned. In other words, there's no alignment between the planets of different solar systems. So they're randomly, their angles are quite random. Mm-hmm. So Ryan's secondary questions to that is, are they aligned to the orbital plane of the Milky Way? The answer is no, because there is no alignment there. And in fact, you've only to look at our own system. Our own solar system's almost at right angles to the plane of the Milky Way, not quite, but kind of very steeply inclined, which immediately answers that it's not a requirement that there should be an alignment with the Milky Way, and in fact that answers the last question in Ryan's email. It's interesting though to look at such alignments. There was a time, it's probably 20 or 30 years ago, it must be more than that actually, colleagues I worked with at the Royal Observatory in Edinburgh thought they could see alignments when they looked at distant galaxies, that they seemed to be aligned in a similar way. And that's been borne out by more recent work that's looked at very distant galaxies. And there are hints of the fact that the planes of these galaxies are all parallel, and it seems to be because they are lying along the filaments of material. We now know that on very large scales, the universe is this kind of honeycomb structure with galaxies lying along the walls of the honeycombs. We call them filaments, and it looks as though there are within a given filament, the galaxies seem to be generally aligned along the filaments. It's still a pretty speculative result, I think, but that's the only kind of alignment that we get with these very large systems. That's not to say that solar system, that's nothing to do with the solar systems of individual stars, but it does tell you that astronomers do look for these alignments and sometimes think they find them.
I suppose the natural tendency is to think we had a big bang, it blew out in all directions and everything would be on the level, so to speak. But over billions of years, things change. You've got different gravitational influences and things merging with other things. And
even that doesn't work, though, because as far as we know, the way space expanded after the Big Bang is isotropically, which means the same in all directions.
Yeah.
And so you've still got that randomness of direction built in there.
Okay, Ryan? You got a big no, my friend. No, and I think, was it only 3 or 4?
Well,
It doesn't matter. But we appreciate the question. Back to the drawing board for you, Ryan. But
it's
at least
worth asking.
know. Yeah, it is definitely worth asking. Well done. Now, we move on to Gordon, who has a couple of questions for us. We're going to have to go back to the first one because it's way too hard. It's way too hard. But he's sort of reflecting on one of our earlier episodes, episode 97's, where we referenced the discovery of Icarus, a star 100 times the mass of our sun, about 9.5 billion light years away. I feel I may be missing something, don't we all? But how is it possible to see the light from a star that would have burned for only a few million years from a distance of 9.5 billion light years? Surely all radiation would have been extinguished and invisible by now. Great question. However, I think I know where you're going to go with this because I think we've talked about it before.
Well, there's kind of two answers to this. First of all, Gordon's absolutely right that something 9.5 billion light years away is going to be very faint. It takes us all our times to see galaxies at that sort of distance, let alone individual stars. This particular star was a very bright one. And also, as I recall, it was gravitationally lensed. So it was sitting behind another galaxy, and the gravitational force of that galaxy, or the gravitational distortion of space of that galaxy, acted like a natural telescope, which is what allowed us to see this single star 9.5 billion light years away, which still I think must be some kind of record breaker. So you're right that the light traveling for all those billions of years has got very feeble because light, it actually follows the inverse square law. It diminishes by the square of its distance from any source. So at that sort of distance, it is very, very faint. But there was a natural coincidence that allowed us to see it. The other side of it, though, is that you're quite right, Gordon, in speculating that this star, and I think this is what you're saying, it didn't burn for very long. It burned for a few million years. In fact, that's exactly what you say. It probably was literally only a few million years. So what's happening there is that if you imagine that star being very bright for a few million years, what it does is it sort of emits a shell of light that is expanding around it at the speed of light. And it means you've got to be in the right place to see that star being bright. And it just so happens that shell has now reached 9.5 billion light years, and we can see it. But if we wait another 100 million years, and some of us will, I'm sure you will, Andrew,
I'm not
and then look
patient.
It'll not be visible because it will have been extinguished. So you're quite right that events in deep space, to find them, if you've got things that are only relatively short-lived, like this star, then you've got to be looking at the right time in order for that radiation to reach your telescopes. The classic example of this is a supernova. Supernovae get very bright, and indeed we can see them at distances far greater than this 9.5 billion light years. They're exploding stars. They get very bright for a very short period, usually a matter of weeks only. And what that means is that you've got to be looking at that time when the wave of light or the pulse of light from your supernova actually passes the distance of the Earth, because then it's gone afterwards.
Yeah, I suppose another way of looking at it is that we probably have missed a multitude of events like this simply because the light didn't get here or we weren't looking when it did.
Yeah, or it's long gone, or
it's long gone. Right. Yeah,
humans didn't exist when the light passed us. Yeah, that's right.
And on another point is we don't know what's around the corner. We don't know what we might see next. The universe is ever changing, and
indeed, that's right. And you highlight something important there, Andrew, because there's a whole new field of astronomy, which is essentially the astronomy of transient events, things that come and go. There is a big new telescope being built it's actually going to be in Chile. It's a large international consortium. It's called the Large
SBVLT, slightly bigger than the Very Large Telescope. Sorry.
It's something like that. It's actually, to be honest, the acronym makes even less sense than that does. It's the LSST, the Large Synoptic Survey Telescope, an 8-meter class telescope, which will, as I recall, it will look at the entire sky every 6 nights.
Wow.
So it takes it 6 nights to measure to observe the entire sky, and then it goes back and does it again.
And on the 7th night, it's rested.
Well, more or less, yes, that's right. I'm sure I've heard that before somewhere.
It might be.
Yeah.
Could be. Okay. Gordon, thank you for that insightful question. It's a good one, and we just happen to be in the right place at the right time to see what we could see. And we do welcome your questions and your feedback and your ongoing support, so thank you for listening. And thank you, Fred, for doing what you do. We really do appreciate it. It's great fun.
Great pleasure, Andrew. Always good to talk, and we'll chat again soon.
We will indeed. Fred Watson, astronomer at large, although I found him. And he'll be back next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.